In this video, we start our study of nuclear physics. So as you go inside the atom, the particle at the center of the atom is the nucleus, and it is positively charged. And we will also study phenomena associated with nuclear physics. An important one is what's called radioactivity. Radioactivity, the term radioactivity refers to emission of radiation from the nucleus. And this radiation that's emitted is called nuclear radiation. A substance that emits nuclear radiation is said to be radioactive. When the radiation was first discovered, the question was if it's atomic radiation. So you have this radiation that's coming out of an atom, and people wondered if this has anything to do, if it's anything similar to atomic spectra, where when electrons go from one energy state to another, there's an exchange of energy. So the question was, is this nuclear radiation, which is now known to be nuclear, but is this radiation the same, or is coming out of those atomic electrons? But there were two observations about this radiation which suggested that was not the case. First of all, the radiation, the nature of the radiation does not depend on the chemical state. For example, if you consider uranium or any other compound of uranium, any salt of uranium, any compound containing uranium, all of these displayed similar radioactive behavior. Chemical states exist at atomic level. So if this radiation was coming from the atomic level with different chemical states, you would expect some differences in these radioactive properties, but that is not the case. So that kind of ruled out that this was an atomic level radiation. The second reasoning was the energies of radiation that these entail were of the order of mega electron volts, MEVs, whereas atomic energies themselves related to transitions are in the electron volt range. So if you'll recall, the ground state of hydrogen, for example, is negative 13.6 electron volts. And all the different energy levels fall in that same region. So if you're getting radiation, if you're getting energies at the order of mega electron volts, then clearly it's very different from what atomic radiation would be expected to have. So that led to the understanding that this radiation that's being observed, radioactivity, is not an atomic level phenomenon, but must involve the nucleus of the atom. There are three types of nuclear radiation: alpha rays, beta rays, and gamma rays. Alpha rays are basically helium nuclei containing 2 protons and 2 neutrons. And this is the lowest energy nuclear radiation. It's least penetrating. You can stop alpha rays by simply a sheet of paper. A sheet of paper can block alpha rays. In terms of energy, more energetic than alpha are beta rays, which are essentially stream of electrons. And these can be stopped by a thin aluminum plate. So it's a stream of electrons, but these are not orbital electrons of the atom. These electrons are actually emerging from inside the nucleus. And we will later on look at this nature of radioactivity, which gives rise to electrons. The third and the most energetic nuclear radiation is gamma rays. It's not a material wave or a mechanical wave, or it doesn't involve traditional matter. It's actually electromagnetic radiation. And this is the most penetrative of all three. It can go through several centimeters of lead or several meters of concrete. So it's the most energetic one. All three nuclear radiations produce ionization in matter because they are of such high energies. In order to ionize an atom, you just need a few electron volts. And here we are talking about a few kilo electron volts to more than 10 mega electron volts as the energy of these nuclear radiations. So all three of them can easily ionize matter. It can ionize atoms and molecules. And as a result, they can interfere with electronics, for example, by causing, now all electronic circuits have a bunch of capacitors, and capacitors, you will recall, are conducting surfaces separated by insulators, either vacuum or air or some other dielectric. So nuclear radiation can ionize the air between the capacitors. So if it becomes ionized, then it's not an insulator anymore, it's a conductor, and thereby it discharges the capacitor, and the circuitry fails, it breaks down, it doesn't function. Because of the ionizing property, all three of the radiations can cause cancer. At least gamma rays are commonly used to cure cancer as well by destroying the tumors involved. The ionizing property of these radiations is used to detect nuclear radiation. The most common type of radiation detector is called the Geiger counter, which you might have seen in movies and stuff. It has a very typical clicking sound, and it's used to detect nuclear radiation. Okay, so starting with the electron, we know there's a nucleus at the center, and then there are orbital electrons around the nucleus. And then when we get to the nucleus itself, it turns out it has a substructure. It has a finer structure than just being one blob of particle. The nucleus consists of two particles, protons and neutrons, and collectively these are known as nucleons. So nucleons are these particles that live inside the nucleus. Both protons and neutrons have the same spin and roughly the same mass. There's a slight difference. Neutron is slightly heavier than a proton. So mass of the proton is 1,836 times mass of the electron, and mass of neutron is 1,839 times mass of the electron. A common unit for mass that is used in nuclear physics is called the atomic mass unit, represented by lowercase u. And the conversion factor is, or we define atomic mass unit as one atomic mass unit equals 1.6605 times 10 to the negative 27 kilograms. The atomic mass unit is defined to make the mass of a carbon atom exactly 12 U. So it's used like a reference. It's a standard. Another convenient unit of mass for certain types of calculations, as we will see later on, is MeV per C square. This is helpful when you're using the equation E equals mc squared, because then the c squares cancel out and you don't have to keep multiplying by the square of the speed of light. And the energy naturally comes out in MeVs. As I said, typical energy in nuclear physics that we encounter is in the range of MeV. So that's a convenient unit for mass here. The conversion factor between the atomic mass unit and MeV per c square is 1U equals 931.5 MeV per c square. There's a table in the book which gives you the masses of the three particles. So you have the proton with the symbol P. This is table 31.2. And it has a mass of 1.67262 times 10 to the negative 27 kilograms. And then this many atomic mass units. And then that's the mass in MeV per c squared. So it's a good reference if you need to use these masses. The term nuclide refers to a specific combination of protons and neutrons. And it's a unique nucleus. So it is a fixed number of protons and neutrons. So it's a unique nucleus. A nuclide is represented by this notation. You have capital X representing the element or the nucleus in question, nuclide in question. And then there is a superscript on the left, a subscript on the right, a subscript on the left, and a subscript on the right. A, Z, and N, all capital letters. Z refers to the atomic number, this one here, or the number of protons in the nucleus. X is the symbol of the element, like K for potassium, etc. N is the number of neutrons in the nucleus, this one here. And then A is the mass number, which is the total number of nucleons in the nucleus. So A is equal to N plus Z. Now, because of this relationship, if you know the value of A and you know the value of Z, you can easily find what N is. So often when you're writing this nuclide representation, you don't write the capital N. Just A and Z is enough to tell you the exact identity of the nuclide in question. Mass of an atom is roughly equal to whatever the value of A is, that many atomic mass units. It's not exact, but it's a good approximation for many purposes. So this is an example of how you show a nuclide. This is a hydrogen nucleus where the number of protons is 1. There are no neutrons, so the number of nucleons, or A, is also 1. If you wrote the number of neutrons, there would be a subscript of 0 on the right of this page. The term isotopes refers to nuclides which have the same Z value but different N's and A's. For example, hydrogen has 3 isotopes, one of which we saw here, which has 1 proton and 0 neutrons. And then there's an isotope of hydrogen which has 1 proton and 1 neutron. and this is called the deuterium, represented by capital D. And then there's a third isotope of hydrogen, which has two neutrons, still one proton, but two neutrons. And that's called a tritium. So hydrogen 1, this is the most common type of hydrogen. Deuterium is quite rare, and tritium is even rarer. A simpler notation for nuclides is where you even omit the Z, the number of protons, you just write the total number of nucleons. This is sufficient because the chemical symbol corresponds to a unique Z value. So if you know the chemical symbol, you can look it up in the periodic table and figure out what the number of protons or what Z is. And then if you subtract it from A, you can find N as well. The nucleus of an atom is a tightly packed ball of nucleons. And in that ball, in that nucleus, nucleons have a large kinetic energy within the confines of the nucleus. So as long as all the nucleons are confined inside the nucleus, they have a huge amount of kinetic energy. They're undergoing vigorous motion. The radius of a nucleus is given by this equation, a constant R naught times the A value, the total number of nucleons raised to 1/3, or the cube root of A. R naught has a value of 1.2 femtometers. Femtometer is sometimes in honor of the physicist Fermi. It's also referred to as Fermi. So R naught has a value of 1.2 Fermis, which is equivalent to 1.2 times 10 to the negative 15 meters. Assuming that a nucleus is like a sphere, we know its volume would be 4/3 pi r cubed. And r, the radius from this relationship, is directly proportional to a cube. But from this relationship, if v is proportional to r cubed, r is proportional to the cube root of v. So the radius of the nucleus is proportional to both the cube root of A and the cube root of the volume. And that means the volume is directly proportional to the A, the number of nucleons. So if you double the number of nucleons, the volume of the nucleus also doubles. And this would be expected if nucleons were tightly packed inside the nucleus with almost no empty space. Let's look at problem number 7. In which we have to find the radius of an alpha particle, radius of an alpha particle. So, as I pointed out, alpha particle is a helium nucleus, which means it has 2 protons and 2 neutrons, or A is 4, which means the radius of the helium nucleus would be using the equation R naught times the cube root of A. This would be 1.2 Fermis times the cube root of 4. So it comes out to 1.9 Fermis. Now, if you think about the the nucleus. In a small, tiny space, you have a bunch of positively charged particles, the protons, and then you have a bunch of neutral, electrically neutral particles, the neutrons. And we know that if you have all these positive particles inside the nucleus, there must be a Coulomb force of repulsion, which are pulling these protons away from each other. So it would be quite strange that a nucleus actually manages to exist with all these repulsive forces inside it. And the reason why you can have a stable nucleus without protons just flying apart because of Coulomb force is the existence of another type of force inside the nucleus, and that is called the strong force or the nuclear force. A strong nuclear force is an attractive force, and it acts between nucleons. So due to the strong force, a proton would attract a proton would attract a neutron, and a neutron would attract a neutron, and a neutron would attract a proton. So all of the nucleons attract each other because of this strong nuclear force. And the magnitude of this force, the intensity, the strength of this force is extremely high for distances which are of the order of the size of the nucleus. So as long as these nucleons are inside the nucleus, they strongly attract each other. But if you separate nucleons to a larger distance, it becomes a repulsive force. And the same thing is true on the other extreme. If you press them too close to each other, this strong force becomes a repulsive force as well. And the relationship between the strong force and distance is an interesting one. At large distances, the strong force almost ceases to exist. It becomes zero. As far as inside the nucleus is concerned, strong force is about 100 times larger than the Coulomb force. So the force of repulsion due to Coulomb force is easily overcome by the strong force, the attraction of the strong force. Since this force is so strong, a large amount of energy is released when a nucleus decays or when it breaks down into its components. And that's the reason why nuclear radiation is of such high energy. It has to do with the huge magnitude of the strong force. There is, in addition to the strong force, there's a third force that exists inside the nucleus, and that's called the weak force. And this one plays an important role in forming the beta particles or in beta decay. Strong force, on the other hand, plays an important role in alpha decay. So alpha decay would not be possible without strong force, beta decay without the weak force. Figure 31.14 shows a graph where on the y-axis you have number of neutrons, and on the x-axis you have number of protons. And then there's a dashed line corresponding to n equals z, number of neutrons equals the number of protons. For small nuclei, we see that the number of neutrons and the number of protons are about the same. But as you get to larger and larger nuclei, heavier nuclei, the number of neutrons start to exceed the number of protons. And this has to do with the stability of the nuclei. So for lighter nuclei, n is equal to z. As nuclei become larger, more neutrons are, so as nuclei become larger, the Coulomb force between the protons is increasing. And therefore you need more neutrons to overcome the Coulomb repulsion, because neutrons don't experience the repulsion, but they do experience the attraction of strong force. So for larger nuclei, there's a greater amount of Coulomb force, and so you need to compensate by that by having more neutrons. So nuclei tend to be more stable when n and z are even numbers. When n and z are even numbers. Nuclei also tend to be more stable when n and z have certain specific values, which are called magic numbers. Magic numbers is reminiscent of how electrons in an atom are, where you have the inert elements on the rightmost column of the periodic table, where all the shells are complete. Similarly, magic numbers in the nuclei refer to or correspond to stability of a shell-like structure inside the nucleus. So this indicates that there is a shell-like structure inside the nucleus. The existence of magic numbers indicates that. So magic numbers indicate a shell structure for the nucleus, which is more stable when shells are full, kind of like how inert or noble elements are, they don't react with other elements because all the shells are complete. Nuclear shell theory has done a good job in explaining nuclear decay and other related properties. So it's an accepted theory in nuclear physics. Okay, we will end here and look at the different types of nuclear decays in the next video.